Hey folks, this is probably the last big idea we're going to encounter, and then we'll sort of run down its consequences and talk more about that, and then do some case studies, but this is the last big idea in proof that we're going to encounter, certainly in Coq. So you can see from the first try name here that this isn't going to work, but let's try to prove this equivalence between our inductive proposition defining evenness and the idea that doubling is the thing that defines evenness. Okay, let's give it a whirl. Let's see where we get. You never know. Okay, NH. Okay, so we need to find. So we know that n is even, and we need to find that there exists some k that's a natural number that n equals double k. So I'm going to say out the gate that induction on n is not going to work because of this sort of like double successor issue, right? It's just not going to work so well. So let's try using this new technique of inversion to see where we can get. So let's do inversion H. Oh, already used. Great. Okay, so we go by inversion. There's two possibilities. Either n is equal to 0, and we used EV0, or it's going to be EVSS. So in the EV0 case, well, this actually seems pretty easy to find, right? 0 equals double k. I know one that does that. Great. Okay, good progress. Okay. Huh. Well, let's see. So we know n is even. There's a number n prime. N is equal to s of n prime. And we know n prime is even. And we need to find a k such that s of n prime is equal to double k. Now, if we knew, so if n prime is even, then well, it ought to be double something. So if there was some k prime which showed that when we doubled k prime, we got to n prime, then successor of k prime would be a good thing here. But we know n prime is even from inversion, but we don't know anything more about it, right? We don't know that there's some k prime for n prime. Now, intuitively, there ought to be one, but we don't have it here. Right? This doesn't quite work. So if you pause for a moment and you look carefully, you'll see that, well, on some level, this is more or less a deja vu moment, right? Like, we know EVN prime. We need to find some k such that s of n prime equals double k. But and if we could know that there exists some k prime for n prime that had the same doubling property, where k prime was half of n prime, then we'd be made. So it's sort of like, well, look, if we just knew the answer for the thing that came before, we'd be good to go. Okay, so the solution here is, as for other deja vu moments, induction. So the idea is you can do induction on evidence, right? Just the same way you do induction on a data type, you can do induction on evidence. Let's run through a concrete example and then see if we can deduce some of the principles of sort of what's at play here. Okay, so here's what we want to show. We have a natural number n. We know that n is even. We need to show there exists some k such that n is equal to double k. That is to say, n is even by our other definition. One tiny note that's only semi-related. If we can show that EVN is equivalent to this, well, then we'd be pretty much made, right? Because we already know that this notion of evenness is equivalent to even b. So then they would all three be equivalent just by transitivity of if and only if. Okay, so we do induction. This works exactly like induction anywhere else. You write induction, the thing you want to do induction on. So here we're doing induction on the derivation E, right? The evidence E that EVN, right? That n is even. And then we list a pattern here. Okay, what goes here in the pattern? Well, it's the same idea as any other notion of induction patterns we've seen before. So there's no arguments to EV0, so there's nothing to write there. The same way there's nothing to write in the base case for nats or for bins or for BTs or for lists, right? There's just nothing there. Otherwise, we have a thing for every subpart. So what shows up in EVSS? Let's look. Let's get back to our definition. Here we go. Well, we'll have one of these. we'll have one of these. And that's it. So there's two parts, right? There's a natural number n, and there's evidence that that one's even. So okay, here's the natural number, we'll call it n prime, because we already have an n. And then here's the evidence that n prime is even. And then we have an IH. So when do you get an IH? Well, when we're doing induction on data, you get an inductive hypothesis for every subpart of the data of the same type. So for a successor, you get an inductive hypothesis for the thing you're a successor of, for n prime. For lists, you get it for the tail, but not for the head. For binary trees, you get it for the left and right subchild, but not for the value. Now here, okay, great. So there's no IH for the number n prime, but we do get an IH for the sub-evidence e prime. Okay. Let's see. What are our cases? So our first case is going to be, well, it's on the rules. It's when EV0 applied. So in that case, we need to find that using no information that there exists some k, 0 equals double k. We've already seen that. Okay, in the next case, let's look carefully at what we know. We have n prime and e prime like we declared. These are the subparts of our derivation. Now, e prime is a subderivation of evenness for n prime, so we get an IH. The IH is whatever our fact is, whatever it is we're trying to prove, but for the smaller thing. So this is exactly what we were missing above. This is the fact that, okay, cool, there is some k prime for that n prime is twice of. How do you say that in English? You know what I mean. There's some k prime such that n prime is double that thing. So let's get it out. So when your IH doesn't exist, I think the natural thing to do is like, you got the present, you open the present. Great, there's some k prime such that n prime is equal to double k prime. Now look what we have to prove. We have to show there exists some k such that s of n prime equals double k. Well, that seems straightforward enough. Our plan was, it's just going to be, well, s of n prime is 2 more than double k prime, so just 1 more than k prime seems to be the right choice. So if we like, we could do this. This will maybe make our lives easier. I think it's maybe more intuitive to say this. Then we say that. Simplify. Those are the same. Okay. That's the gist of it. Just as before, so this is easily a very confusing concept. But I want to stress that it's really not at all different from any of the inductions we did on anything else. Okay, the thing we're doing induction on is a different kind of thing, right? It's this derivation, this proof, rather than some object that we're manipulating like in our programs. But the structure is exactly the same. The subparts get IHs, the tactics look the same, and it sort of lets you work in sort of the usual way. What I want to note here is, in the past, doing inductions to reason about evenness has been really annoying because of this sort of two-step problem, right? That you don't go just down by 1 each time, you go by 2. But what induction on an inductive proposition let us do was only consider the cases that are actually defined. So I said this up front, that what's great about inductive propositions is they let us only talk about the good ones. They let us reason only about the parts we care about. And that's exactly what induction here let us do. By doing induction on evidence, we were able to say, look, the only 2 cases I care about are EV0, EVSS. I never had to even look at an odd number to prove this property. That, I think, is pretty cool. Okay. We got a ton of practice for you here. Be patient with yourself. Like, think back, like, what was it like when you first learned induction, like a week or 2 ago? Okay, be patient. Like, it's going to take a minute to get fully comfortable. That's really very normal. The rest of the file is just case studies. We're just going to look at different inductive propositions, define different things with them, see what they're for, define a bunch of useful stuff we'll need for our case studies later on, just try to get some good practice with them. And then we'll spend the next 3 days after this just doing case studies, and that'll be it for Coq. So I think you'll get plenty of practice building up sort of strong inductive muscles here, and I look forward to seeing how y'all do. Cheers.